Live on YouTube. Ma'am, we are live on YouTube, so you can start the meeting.
Okay. Welcome everyone to the third and last day of this workshop. I request Dr. Dft Chako to chair the session, the morning session today. We have two speakers, Dr. Shobna Narasimhan and Dr. Pratish Kumar, who are with us. Dr. Chako, you have to unmute yourself.
Yeah. Good morning, all of you, and welcome to the last day of this wonderful journey through the challenges in theoretical sciences. Today morning, we have a couple of interesting sessions by two eminent scientists from two different fields. One is theoretical, one is material science, and another is astrophysics, computational astrophysics. This morning we have Professor Shobna Narasimhan delivering the first talk. She completed her after her MSc from IIT Bombay. She went to Harvard University to pursue her PhD in theoretical physics under the supervision of Professor David Vanderbilt. She did her postdoc from Brookhaven's National Laboratory, USA, and at Fritz Haber's Institute of Max Planck Society, Berlin. And then she joined the theoretical science unit of Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore, as a faculty member in 1996. Since then, she has been continuing with the institute, and now she is a professor at the same place. She was also formerly the chair of the theoretical science unit and the dean of affairs at the JNCSR. She has also held various positions at many institutes, which include the University of Cambridge as well as the University de Paris Diderot. She has been very keen and promoting participation of women in science, and has been a member of the working group for science and physics of IUPAP. In fact, she has also organized several career development workshops for women in physics at various at institutes places such as ICTP, Italy, as well as East African Institute for Fundamental Research, Rwanda. She has several. She is a master lecturership of American Physical Society. She is also a fellow of Indian Academy of Sciences, as well as she is a fellow of National Academy of Sciences, India. She also received. She is also an international honorary member of American Academy of Arts and Sciences, and has received several awards such as Kalpana Chawla Award, the Material Sciences Society of India Award medal, as well as the International Union of Material Science Society Young Research Award, and the Institute Silver Medal of IIT Bombay. She will be talking on materials design from first principles. We are very grateful to have you, madam, and we would like you to now take over the stage and start your presentation on designing materials from first principles. Thank you.
Okay, thank you very much. Something really weird just happened, which is a wasp came and stung me just now, so I don't know what to do.
We can stop, wait for 5 minutes if you want to.
Yeah. I think I have to get it attended to. Hello? Hello? Who is speaking? My sister, do you think you can come to my office? I'm giving a talk, but a wasp just came and stung me, so I need to get it attended to. I'm very sorry. The doctor is saying I have to go see her. So it will take about 10 minutes. Is that okay?
Okay. Okay.
I'm really
Yeah,
very sorry. But it's paining really
So
badly. So shall we just say that?
Please go ahead.
Or
10 minutes.
I don't know whether I can just try. Okay, I'll try. I'll start, and if it becomes really unbearably painful,
I think.
I don't
Shobna,
know.
okay. Shobna, please go ahead. It's okay.
Okay.
We'll wait. We'll wait.
Okay.
Chapo, so can we put an announcement on this screen that we'll start in 15 minutes? The lecture will start in 15 minutes.
Okay, yeah, let me check. Let me put that in.
I am back if you want me. Hello?
Welcome back.
Yeah.
Do you want me to give my talk or what do you want me to do?
How are you feeling, first of all?
Okay, I'm in some pain. It was a honeybee. So they've given me a painkiller and an anti-allergic thing and some ice. I can talk.
Are you sure? Otherwise, we can.
No, I'll talk. You just tell me if you want me to cut it short to half an hour or should I talk for the full hour?
No, you do whatever suits you because you should feel good.
Okay, so I'll start and I'll see. Oh, it's gone, you think? Okay. All right. So I'm very sorry this happened. This is the price we pay for having a campus surrounded by beautiful gardens. So there was a honeybee and it bit me just as I was about to start speaking. So I'm in some pain, but I think I will manage. So I'm very happy to give this talk. And I'm especially happy because of something that was not mentioned when introducing me, which is that I'm also an alumna of Bombay University. I grew up in Mumbai and I got my BSc from the University of Bombay, as it was called then. So let me share my screen now. Can you see my screen?
Yes.
Okay. So I'm going to talk today about materials design from first principles, which, as you will see, is a topic that has both theoretical and computational elements in it. I had planned my talk for 1 hour. Maybe I'll try to cut it a bit short because of this unfortunate delay. So about me, I'm a professor in JNCSR Bangalore, as you heard. In case you haven't heard about JNC, it's a research institute in Bangalore. And something that we're very proud of is that when Nature Index ranked institutions worldwide, normalized by their size, JNC actually came out 7th. We came ahead of some very famous places like Princeton University, etc. So what we do in my group is we aim to design new nanomaterials on the computer using first principles techniques of density functional theory and a process of rational design. Some of these terms, some of you may not be familiar with, but I will explain them. So first, I want to tell you a little bit about materials science. So materials are so important to us that we define human history and progress by the materials that we use in a given era. So you have the Stone Age, the Copper Age, the Bronze Age, the Iron Age, etc. And remember this Bronze Age because I will talk about it in a minute. How many materials are there in nature? So this is, of course, the periodic table. And we have 98 naturally occurring elements and about 4,000 naturally occurring minerals. That is either elemental materials or compounds of these materials that occur naturally. However, why material science is of such great interest is that we can make new materials. So these Lego blocks have been made into the periodic table, and the elements of the periodic table are like building blocks that we can play with to make new materials. So how many materials can we make? So these are a series of books called Landolf-Bernstein, which contain the materials that we've already made, and there are huge numbers of them. So it's been estimated that if you look at all the crystal structures possible and the various stoichiometric compositions, there are about 10 raised to 11 potential quaternary compounds, that is compounds containing 4 elements, and 10 raised to 13 quinary compounds, that is compounds containing 5 elements. So this is a huge space in which to search. So how does one make new materials? So think of bronze, which I mentioned. It's an alloy of copper and tin. And it's harder than copper alone, and it does not rust. So that's why bronze is important. And these, for example, this is the famous dancing girl of Mohenjo-Daro, which we studied in school, and you can see in the museum in the Mumbai. I forget what it's called now. It used to be called the Prince of Wales Museum when I lived there, but now it has some other name. And how did they know to make bronze? Okay, now my screen is frozen for some reason. Okay, so all the materials that we use today. So there are some of them were discovered by accident, and many of them were discovered by a very tedious process of trial and error. Okay, so for example, there's a famous material, which is the Haber process for the synthesis of ammonia from nitrogen and hydrogen. I'm sure most of you are familiar with this process. It has been suggested as the most important scientific discovery of the 20th century. And in this synthesis, we use iron as a catalyst. How did they know that they should use iron? They just tested by brute force about 2,500 materials as the possible catalyst, and then decided that iron was the best. But can we do better than that? That's what we want to do now. We want to replace this trial and error or brute force method by what is called rational materials design. So for rational materials design, you need a to and fro between theory and experiment. So let's come to computation and theory. Why do we do computation? I'm a computational scientist. So why do we want to do computation at all in this field? First of all, it is cheaper. Computers are so cheap now, and experiments are often so expensive that it is often cheaper to do the computation. I can work from home because this is partly a joke, but also partly serious. Believe me, in the past 1.5 years, I really grew to appreciate the fact that I could work from home. It is often quicker because computers have become so fast that you can do a computation on a material much faster than you can do the synthesis of the material. You can get a greater understanding. One can simulate conditions that can be very difficult to achieve in a lab. For example, if you want very high pressures, that can be very hard to do in a lab, but in a computer, you can do it relatively easily. We can switch off certain effects. If we want to see what is the effect of relativity, what is the effect of magnetism, something like that, we can switch them on and off in the material in a calculation, which you can't really do in the experiment. And we can make predictions for experimentalists to verify. So this is a poster of a movie, Journey to the Center of the Earth. So when I said we can achieve conditions difficult in the lab, for example, there's still an on-running debate about what is the phase of the iron in the Earth's core. And this is something you can't really do an experiment about. You can't go into the Earth's core and find out. You can do lab experiments, but they're sort of hard and controversial. But you can subject iron in a computation to high pressures, similar to what it would have in the center of the Earth, or methane to what it would have in Jupiter or something, and see what phase it would have. So how do we do rational materials design? We take material A, material B, material C, we do computations on them. Then we analyze these results. By the way, these pictures are from a comic strip called PhD Comics. So if you haven't already seen it, I would urge you to go look at PhD Comics. It's available online. Then we obtain insight into design principles. And then using this insight, we can on the computer make a new material which may have certain properties that we desire. So what kind of computations do we do? What we do in my group is something called density functional theory. So I will tell you a little bit about density functional theory in case you don't know it. So the basic problem we want to do in condensed matter physics or in material science is to solve the quantum many-body problem. So our many-body system consists of some number of nuclei and some number of electrons, which interact via the Coulomb interaction. And examples can be atoms, molecules, or condensed matter systems. And so to learn about its properties, we have to solve the many-electron Schrödinger equation. And of course, the solutions must be properly antisymmetrized and satisfy the Pauli exclusion principle. The problem is that this is very, very difficult to solve because it is a many-body problem. So what does the Hamiltonian look like? If we have a material with n nuclei and n electrons, then you have the kinetic energy of the nuclei, the kinetic energy of the electrons, interactions between the nuclei and the electrons, and between the electrons. So usually we make the Born-Oppenheimer approximation so that we can separate out the electronic Hamiltonian. So the electronic Hamiltonian has the kinetic energy of the electrons, the interaction between the nuclei and the electrons, and the electron-electron interactions. And it is these electron-electron interactions, which are a many-body term, that makes this a hard problem to solve. So density functional theory is a way of including these troublesome electron-electron interactions. So when you have to solve this many-particle Schrödinger equation, then those of us who do condensed matter theory basically follow one of two approaches. There are those who do many-body theory and those of us who do density functional theory. Those who do many-body theory retain the many-body nature and use a model Hamiltonian, for example, the Ising model or the Hubbard model, uses suitable parametrization and then solve it numerically or analytically. Whereas those of us who do DFT map it onto a one-particle Schrödinger equation. This mapping is exact in principle, but approximate in practice. We have no free parameters, unlike in many-body theory, and we solve this numerically. So let me tell you more about this. So in density functional theory, we solve something called the Kohn-Sham equations, which map the many-electron problem onto an equivalent one-electron problem. So to tell you about this, I'm going to use a somewhat frivolous analogy. So it's as if we have a system of many people. So you can think of the blue men as the nuclei and the red women as the electrons, and they have complicated interactions between them. And the problem we want to solve is that we want to arrange all of them so that globally the optimal level of happiness is achieved, which is clearly a very hard problem to solve because it's a many-body problem. And in DFT, in the Kohn-Sham equations, this is replaced by this problem where you have just one woman, one electron, and you have to put her where she's happiest, which is obviously a much easier problem to solve. Now, what price do we pay for solving, for replacing this complicated problem by this simple problem is that there's an extra term in the Hamiltonian called the exchange correlation term. And I have graphically denoted that by putting these face masks on these men. Okay, and the problem we have is that we don't know yet the exact form of this exchange correlation term. So when Professor Mishra asked me to give this talk, she asked me to mention challenges in the field. And one of the challenges that still remains is to know what is the exact form of this exchange correlation term. We don't know it yet. So the person who developed this theory is Walter Kohn, who has a very inspiring personal story. He had to escape from Austria, from the Nazis when he was young because he was Jewish. He was sent on these trains called Kindertransport to England, where he was then imprisoned as an enemy alien. And it was while he was in a prison camp in Canada that he became interested in mathematics and physics. And for developing DFT, he got the Nobel Prize in 1998. This is a list of the papers in the PhysRev journals, PhysRev Letters, PhysRev B, PhysRev A, which have the most citations. And the top 10 papers, which are the most cited, are all connected to DFT. So you can see that this is a very active and very popular field. The papers by Walter Kohn, the Hohenberg-Kohn and Kohn-Sham papers, are not at the top of the list. And the reason they're not at the top of the list is that they're such famous papers that usually people don't bother to cite them anymore. Now, I mentioned to you that there is this outstanding problem, this problem that remains to be solved, of designing the perfect mask, finding the exact form of the exchange correlation interaction in that term in the Hamiltonian, into which we've dumped all the many-body nature of the problem. And certainly anyone who solves this problem is pretty much guaranteed to win a Nobel Prize. Okay, so what do we do? DFT calculations are also called first principles calculations because they have no empirical input. Okay, the only input into the calculation is atomic numbers and atomic masses. And then you grind through the machinery of DFT and you get your output. And what is the output? So you input structure and composition. You do the DFT calculations. Depending on your system, the calculations may be very fast. It may be just a few seconds, or it may take a few days. And the output is mostly very accurate results for the total energy of the system and various properties of the system. So what kind of properties can we calculate? We can get the total energy, which is a very useful quantity. You can use it to calculate geometric structure. You can get the charge density. We can also get electronic eigenvalues. For these two, I put a smiley face. For this, I put a sort of puzzle face, because these two are formally guaranteed to be exactly correct, whereas these don't have that formal justification, but we still use them all the time and it works out pretty well. DFT codes can be run on many platforms. This is a picture from already many years ago where one of my friends, Nicola Marzari, ran a DFT code on his cell phone. I just want to, before I start giving you results from my work, I want to say a little bit about why I work in the field of nanoscience. So this is, of course, a Tata Nano car, but we can also have truly nano cars. So what are the advantages of going nano? One is, of course, miniaturization, but it also has the big advantage that you need less amount of possibly costly materials. For example, the catalysts that you have in cars are materials like palladium, platinum, rhodium, which are extremely expensive. And if you need smaller amounts of them, it's a huge advantage. You have enhanced properties, such as a higher magnetic moment, or more reactive when they're in nano form than when they are in macroscopic form. And at this level, every single atom counts. For example, this is the reactivity of a gold catalyst. You may be surprised that I'm talking about gold, because gold is something you normally think of as not being reactive. However, gold, though it's not reactive in bulk form, becomes reactive in nanoscopic form. And see, 8 atoms in a nanoparticle, gold nanoparticle, it's pretty reactive. 7 atoms is not reactive. 9 atoms is less reactive. So every atom counts at this scale. Similarly, if you have what is called phosphorylene, it's a layered form of phosphorus. You can see that depending on the number of atomic layers you have, you can tune the band gap. So every atomic layer makes a difference, every atom makes a difference. So now I'm going to give you 5 examples from our work on designing novel nanomaterials to show you what are the kinds of things that we can do. So we aim, this is the same slide I showed you before, but now hopefully the words are making more sense to you. So we aim to design new nanomaterials in silico that's on the computer using first principles techniques of density functional theory and a process of rational design. So I will give these 5 examples of how you can make a new material, tune charge, tune morphology, tune reactivity, tune diffusion and stability, and tune rotation. So first example, I want to show you, can we make a new material? So I told you about bronze, which is an alloy of copper and tin. Now you can make alloys of many metals, but you cannot, for example, make an alloy of iron and gold. They are immiscible in the bulk. You can't make an alloy. But from our calculations, which were done by my former student, Madhura Marathe, we predicted that iron and gold will form a stable surface alloy if a single atomic layer is co-deposited on a ruthenium substrate. And then our experimental collaborators, the group of Sylvie Rousset in Paris, did the experiment, and indeed this they were able to make. So this here is an STM image. Every black dot here is an iron atom. Every bright dot here is a gold atom. So every iron atom is surrounded by 6 gold atoms, and it forms this iron gold surface alloy. This is our theoretical simulation of what the STM image of this alloy would look like. And you can see we have a very good resemblance between the experiment and the theory. We can also find out why this alloy forms. And I told you we can switch off certain effects in our calculations. So one of the effects we could switch off was the magnetism of the iron atoms. And we found out that if we switch off the magnetism, the alloy does not want to form. If we switch it on, it forms. So what happens is that when this alloy forms on the surface, but not in the bulk, these iron atoms can have a very high magnetic moment, and that lowers the whole energy of the system, and that's why this alloy forms. Now I'm going to tell you about, can we control the charge state of a material? Okay, so this is a molecule called cobalt phthalocyanine. There's a cobalt atom sitting at the center, which is usually in the 0 charge state. But if you can make it charged with 1 electron, it becomes a beta catalyst. So how can we do that? You deposit it on graphene. It's still in the 0 charge state. But if you can dope the graphene with not 1, but 2 nitrogen atoms, then charge is transferred from the nitrogen to the cobalt, and it becomes negatively charged. So this calculation was done by my student Saurav Mondal. So here, these red lobes that you see are negative electronic charge. Blue is positive charge. So you see that if you have just 1 nitrogen atom, only a little bit of charge is transferred. But if you have 2 nitrogen atoms in the graphene, then a significant amount of charge is transferred to the molecule, and the cobalt becomes negatively charged, and then you expect it to be a beta catalyst. So now I'm going to talk about a third example where we think about not just can we change the charge, but also can we change the shape of a material. So I told you that gold is used in nanoparticle form as a catalyst. So large gold nanoparticles have these 3-dimensional shapes, which is true both in the gas phase and when they are deposited on oxide substrates. However, there's reason to believe that there will be better nanocatalysts if they can instead be made to take a 2-dimensional planar shape. Okay, so our main goal is to flatten the curve. That's a silly COVID joke. Sorry, we want to flatten the nanoparticle. So to say it again, if you have you can have a three-dimensional form of this 20-atom gold nanoparticle, which is our model system, and a planar form. And usually this one is lower in energy, and that is why it is formed. But this, though it's high in energy, we believe it will be a better catalyst. Okay, so can we flip the seesaw? Can we make P lower in energy than T? And previous authors have suggested various strategies. And this is again a COVID joke that one way of flattening the curve is you just stay in bed and your curve flattens. So returning to the serious science, this calculation was done by my student Nisha Maman. And we suggested that if you deposit this nanoparticle on magnesium oxide, then it has this three-dimensional form. But if you dope the magnesium oxide with an electron donor, for example, if you replace some of the divalent gray magnesium atoms with these trivalent purple aluminum atoms, then you will see this change in morphology. Incidentally, if you look very carefully here, you will see Nisha is wearing two earrings. One of them is the flat nanoparticle, one of them is the three-dimensional nanoparticle. Okay, so we did the calculation and we saw that for small dopant concentrations, you still get the three-dimensional form, but for dopant concentrations greater than about 0.5%, you get the flat nanoparticle being favored. And then very soon after our experiment was, our calculation was published, the experiment was done. It was done by the group of Freund in Berlin. So they took a slightly different system. They took calcium oxide instead of magnesium oxide. So when they deposit gold nanoparticles on this undoped support, this is again an STM image. You see you have these three-dimensional shapes for the clusters. And then when you dope the support, in this case, they used molybdenum as the dopant. Instead, you get these flat nanoparticles. So this strategy works. So we made a theoretical prediction, and then the experiment confirmed the prediction. Okay, and why does this happen? Again, it is because charge is transferred. So these red lobes show electrons that have been transferred from the support to the nanoparticle, which then flattens out. Now, I said that the reason for this, that we want to make this, is because it will be a better catalyst. So can we see if it is indeed a better catalyst? So the simple model reaction we take is we put an oxygen molecule here. These are the two blue spheres are the oxygen molecule. And then we stretch the molecule to dissociate the oxygen. And using DFT, we can calculate how much energy it takes to break it. So this is how the energy of the system changes as you pull apart the molecule and break it. And this energy from here to here is the dissociation barrier. And we can see that on the undoped support, when you have the three-dimensional form, it takes 0.68 EV to break it. But on the doped support, it takes much less energy. That's what the catalyst does, okay? The catalyst lowers the barrier to break a bond. So this is a better catalyst than this. So changing the shape made it a better catalyst. So now I come to my next example, where we talk about whether we can understand diffusion and stability of a material. Okay, so here, this over here is an electron micrograph of gold nanoparticles on an oxide support. Now, here you see that these clusters of nanoparticles are moving and they're fusing together. Two of them fuse together here. If you watch longer, you will see these two will also fuse. This is called sintering. Nanoparticles are always unstable with respect to sintering. They move, they diffuse, and then they sinter. And this means that you lose the advantage you had of having made a nanoparticle. So we want to study this process. Okay, so to do this, we studied various nanoparticles. I'll show you examples for platinum. So this is not just some fancy animation, artistic animation. This is actual science. We've seen that if you have a platinum nanoparticle, this is how it moves on the oxide support on MgO. This is what's called a hopping process. And we can calculate the energy it takes to move along the surface. So this energy here is the diffusion barrier, which is 0.88 electron volts. Now let's change it. I told you every atom matters at the nanoscale. So instead of one platinum atom, let's take 2 platinum atoms. And now it doesn't just hop. You see, it does this cartwheeling mechanism. It lies flat, then becomes vertical, and then lies flat again. And it takes much less energy to do this motion. It is now, before it was 0.88 eV, now it's 0.42 eV. Okay. Now, if we add one more atom, 3 atoms, then it does this funny walking motion, which I decided to call AT-AT walking. I don't know if any of you are fans of the Star Wars movies, but in the Star Wars movies, there are these transports called the AT-AT walkers. And this motion reminded me of that, and the barrier is 0.6 eV. Now we add one more molecule, one more platinum atom, and have 4 platinum atoms. And now you see it has a sort of rolling motion. Okay, so we get the barriers for the diffusion. And when we look at these barriers, we see that for the monomers, dimers, tetramers, that is if you have 1, 2, or 4 atoms, then this diffusion barrier scales with the bulk melting temperature of the bulk metal, which was a very unexpected result. Okay, because these are tiny little particles. You wouldn't think things would scale with the bulk melting temperature. But the scaling relation does not hold for the dimers. And we have an understanding for why this happens, which I don't have time to go into now. And we can also study the process of sintering, that is of fusing together, because we have these dimer diffusion barriers, and we can study the energetics, etc. And so we see, for example, if you see how platinum nanoparticles sinter and grow bigger, they grow bigger by having 1 atom at a time added. Now, when you have 1 atom at a time being added, you would normally think it would be the single atom which would diffuse and join the bigger particle. But we find that for platinum, it is the bigger particle that diffuses and joins the single atom. Whereas for gold, it is different. For gold, it is by a process that's called particle migration and coalescence. Now I come to my last example, which is, can we understand the movement of what are called molecular machines? So there are molecular machines called molecular motors. These are natural or artificial molecular machines that are the essential agents of movement in living organisms. And we also want to make artificial ones. So this over here is an example. This is again an STM image. It's a molecular rotor. That's a class. They rotate under an energy input. Okay, so this over here is a guest molecule, and this over here is a host molecule. So we have studied a certain kind of molecular rotor system. So here I have gray molecules, which are the guest molecules, and yellow molecules, which are the host molecules. This is again an experimental STM image. Both are of the same species. And oops, I'll play the movie. You can see that the guest molecules are rotating, but they're not rotating smoothly. It's a kind of switching rotation. They abruptly rotate between various positions. Let me show it to you again if I can. I have, yeah, you can see they rotate. Okay, so we wanted to study this process, how it happens, why it happens, how much energy it costs, etc. And for that, my student Abhishek Adak did this calculation. This movie is the result of DFT calculations. So over here, you see the rotation happening in this picture over here. Okay, again, I've lost my cursor. I don't know where it's gone. So the picture shows you the rotation, and the graph at the bottom shows you how the energy of the system changes during the rotation. So these green and yellow lobes are hydrogen bonds that are formed between the guest molecule, which is rotating, and the host network, which is static. And when hydrogen bonds form, the energy of the system gets lowered. And when these hydrogen bonds are not there, the energy is higher. And so you see, you have this rotational energy landscape. Okay. And we can also calculate this energy barrier. So on the left is the same part of the same video you just saw. We've calculated the rotational energy barrier. And from DFT, we get it as 0.944 EV. And from the experiments, by repeating the STM experiments at various temperatures, they get an estimate of 0.95 EV. So these two are in excellent agreement with each other. So once again, you see that DFT is now at a state where you can do very good numerical estimates of quantities also. So we can design materials, we can calculate barriers, we can do a lot. So the take-home message I wanted to leave you with is that density functional theory, when used in tandem with experiments, can be used very successfully to understand why materials possess the properties they do and design novel nanomaterials with desired properties. The acknowledgements, the first group of people are students who did their PhD with me and worked on these. Stefano De Gironcoli, we worked, he's at CISA in Trieste, Italy. We worked on the gold nanoparticle work. The next is a group of people in Paris who did the experiments on the surface alloys. The next is a group of people in Munich who did the experiments on the molecular rotors. And then finally, we have the funding agencies and the people who give us computational resources. Thank you very much. I did sort of rush through my talk. I'm aware of that. I apologize for that. The reason I rushed was that we lost a lot of time in the beginning due to that bee stinging me. And I didn't want to take away too much time from the next speaker. So I talked a little fast. So thank you very much. And I'll be happy to take questions.
Thank you, Professor Narasimha, for a wonderful insight into overview of what material science, what are the challenges and interesting things that one can pursue in the field of material science, computational material science. The session is now open to all, and if there are any questions, you may raise your hands. Yeah. Tanay Kona, please.
Hello, good morning, ma'am.
Yeah.
Myself, Tanay Khona. I am pursuing my master's in material science from University of Mumbai.
Okay.
So, ma'am, I have two questions. The first was you showed that movement of platinum atoms, like we add one atom. So, ma'am, in detail, can you tell how that was observed actually?
So, I mean, you can observe it with STM, but what we did was we did the calculations. So what you do is you take, say I take 3 platinum atoms, okay? I put them together and I place them on the surface and I do various calculations to first find what is the lowest energy configuration. For example, do they want to form a triangle? Do they want to all sit in a straight row? What is their most favored position with respect to the surface, etc. Okay, so that is the global minimum state. Then there will be many global minimum states. Like in one unit cell, there's a global minimum, then it can go to the next unit cell and form the same global minimum. So when it moves on the surface from one global minimum to the next global minimum, it has to pass through a transition state. Okay, so to find the transition state, the transition states are what are called saddle points in the energy landscape. And there are various algorithms to find these saddle points. So we use something called the nudged elastic band, which is an algorithm which helps you find these transition states. So we do a calculation. We say you have to move from this point to this point, find the lowest energy path to move from that. And so when we find that, then we find this walking and this rolling and all that. And so that's how we find it. Okay, so there's some question in the chat box. Are these technologies, can somebody read the full message to me? Are
Yeah.
these technologies also used for
Maybe I can ask.
yeah, so certainly material scientists do use materials for spacecraft. I'm not an expert on what alloys are used. I know, for example, that for aircraft, you use various aluminum alloys. I mean, there's a whole field of metallurgy where you make alloys that have to be light but strong. So there is a whole field of material science just devoted to that. And if you're using it for spacecraft, then in addition, they have to withstand high temperatures, because if you have re-entry, etc., then you are subjected to very high temperatures and high stresses. So certainly these technologies are used for that also. Are there any other questions?
Yes, ma'am. Thank you for your response for last question. Ma'am, one more question is, like, in the introduction, we got to know about your journey in this field. But if you yourself can tell after your +2 level, how, like, what subjects made you interested and how you ended up in this field? Okay. And what skills you felt that, like, one is computational skill, what skills you felt that are important for this field?
Okay, so that's a nice question and I will answer it. So, okay, I did my ICSE 10th standard. And then at that stage, I wasn't really sure what I wanted to do. I didn't even know whether I wanted to do arts or sciences, okay, because I like both. And then I thought I'll do science. I mean, I did well marks-wise, so people thought I was crazy to even consider doing arts, but I liked art subjects also. But the reason I decided to do science was I thought it's easier to be a science student with an interest in art subjects than an art student who is also interested in science subjects. So I went to +2, and at that time, I didn't like physics at all. In school, I had not liked physics, maybe because I didn't like my first physics teacher and she didn't like me. So I asked them if I could drop physics, but they said, no, if you're a science major in HSC, you have to take physics. So I took physics, maths, chemistry, and geology. Okay. And then that time there was the birth centenary of Albert Einstein, and someone asked me if I will do a radio program for school children about Einstein. So then I started reading up about Einstein, and I learned about quantum mechanics. Also, that was when we were first exposed to quantum mechanics in our classes. And I also learned about special relativity. And these two things just fascinated me, and I decided I wanted to do physics. And after that, I was just totally in love with physics. And I decided I wanted to become a physicist. And I didn't, even though I got good marks in my +2, I didn't even consider doing engineering or anything. I only wanted to do physics. So I joined St. Xavier's College in Mumbai for my physics BSc. But I did lots of other things also in St. Xavier's College. I used to write, I used to do plays, I used to do, I took some courses in some film appreciation, music appreciation, all kinds of things. And then I went to IIT Bombay for my MSc. And then I went to Harvard. And at that point, I thought I was going to do astronomy or astrophysics or particle physics, high energy physics. I had not at all thought about doing condensed matter or material science. But when I went to Harvard, I was taught some courses by very good people doing condensed matter physics. And that's when I first decided to do it. But even at that stage, I thought I wanted to do analytical work rather than computational work, because I had never used a computer. Okay, in that time in IIT Bombay, we had to do a computer course. You will all laugh. We didn't even use the computer. There was one big mainframe computer where they had punched cards. We used to write the code by hand. We used to give it to an operator who will punch it in and run it. So I had no experience with computers. Whereas my classmates who were at Harvard, who were all grown up in America, of course, knew computers. So I was very intimidated by computers. But slowly I got interested in it, and that's how I ended up as a computational scientist. I have no regrets. I'm very happy with what I'm doing. I find it very interesting intellectually, and I also like the fact that it's of some practical use. I like the fact that it is both intellectually appealing and useful. Okay, that's my answer. Is that answer your question?
Yeah. So,
someone called Sunil Ekwade has raised his hand.
Okay.
Yeah.
Oh, yeah. Yeah, Sunil, please go ahead and ask your question.
Yes, ma'am. Actually, I wanted to ask that how do we add a single atom in the system or a molecule? It is just a computational part, or we actually do it in the lab or something?
Okay, so you can do it both ways. Of course, in the computation, it's very easy to do, but they also do it experimentally, which is what is remarkable about it. So in experiments, there are different ways of doing it. There are people who can do it by wet chemical synthesis, but there are also people who do it by, for example, they hit a target, a metal target with something with a lot of energy, so that these metal nanoparticles are formed and break off. And then they use a mass spectrometer, which can very accurately measures the mass of these, with atomic precision, so that you can get size selected nanoparticles, which are all have, exactly the same number of atoms. So you can do experiments as well. Of course, we haven't yet achieved the ability to do this at an industrial scale, which is what we would ultimately want to do. But in the lab, people can certainly do it. Does that answer your question?
There was one more question. I think I don't, because Gupta had raised. Would you like to ask the question? Well, there's one question which I would like to ask, really mainly from the students' point of view. A lot of students would really like to understand the career in this field of computational material science. In fact, it has a good career opportunities, but maybe if you can comment on the career opportunities in the field of computational science. computational material science that will be helpful to students to pursue careers in this field?
Yeah, so this is a field in which you can do both work in academia and in industry. Of course, the academic career path, you would do a PhD and then a postdoc and then look for a job in a research institute or a university or a college or something. But also increasingly industries are beginning to realize that if they have people doing computation, then they can work together with the people making materials and guide them. So all the big companies like, whatever, GE, IBM, Shell, they all have research centers also in India and abroad, of course. And also many of the Indian companies, for example, I don't know, Bharat Petroleum, TCS, they all have industrial labs where they are beginning to hire theorists to do computations. If you're going into this field right now, like in most fields, one of the really hot trends is to do machine learning. That's something I didn't talk about. I was wondering whether to put in something about it in my talk, but then I didn't put it in. But to combine techniques of machine learning with material science and the search for materials, properties, materials design is really a very, very hot topic now. And if you have some training in physics combined with expertise in machine learning, you will just be snapped up on the job market, both the academic job market and the industrial job market. One of my PhD students, former PhD students, for example, is working in industry doing this kind of work right now.
Thank you, ma'am, for giving us that understanding of.
Question: can we use these techniques of computation for finding allotropic compounds? Yes, certainly you can. And this is, again, a very hot field. So for example, I'll just give you one example. So you have all heard of graphene, I suppose, which is a single layer of carbon of graphite. But there is, for example, there's phosphorylene, which is a single layer of phosphorus atoms. So there's, again, a very hot material right now is what is called blue phosphorine. So black phosphorine is a single layer of what's called black phosphorus. But blue phosphorine is an allotrope of phosphorus, which is also a single layer. And that was something that was first suggested computationally. People made it on the computer and suggested that if you could make it, it would be stable, it would have these properties, it would have this band gap, it would have this structure, etc. And then people started to make it, and they had mixed success, but there are reports that people have synthesized blue phosphorine. So certainly you can predict allotropes on the computer, and then people can try to make them.
Any more question? Think, yeah. So if you have no more question, we thank Professor Shobna Narasimhan for the wonderful insight into the field of material science, computational material science, or material science using first principles, and what are the opportunities, what we can do, and what kind of problems can be solved using this computational methods, and what are their opportunities in both industries as well as academics. Yeah, thank you very much, madam, for
Thank
this
you so
talk.
much. And I apologize again that there was this unfortunate thing that happened at the beginning of the talk. And actually, throughout this talk, I've been holding my finger like this because it pains quite badly. So I'm sorry if the talk also was a little shaky.
In fact, no, in fact, madam, in spite of this pain, you gave us a wonderful talk. This was an accident. It was at the last moment, just before you started the talk.
Yeah.
So it was, and being stung is really extremely painful. So,
Yeah, it is hurting.
and in spite of that, you gave us the talk. And thank you very much, ma'am.
Okay, bye.
Yeah, thank you. Uh, yeah, the next speaker is there. Dr. Pravesh Kumar, we have, maybe we can just start to, you can check whether you are able to share I think, yeah, you are the host, so you should be able to do the presentation. So shall we start right now, or maybe we can wait for a few minutes, maybe a couple of minutes? Hello, Dr. Kumar. Yeah, are you able to? Okay, yeah. Before we start, maybe I would like to introduce the speaker. This the second talk is by Dr. Pravesh Kumar from ICTS Bangalore. We have we have a very interesting talk on the field of computational challenges in computational astrophysics with black holes. I'd like to introduce the speaker. He did after he did his engineering from Birla Institute of Technology, BITS Pilani, and then he went over to Cyprus University, New York, for his PhD. He did his PhD in the field of gravitational wave astrophysics. During his uh, uh, engineering, as well as later on, he had opportunities to work with several variety of institutes such as IIT Bangalore, where he did his intern. Then he was a visiting scholar at the Max Planck Institute for Gravitational Physics, Germany. He also had opportunity to work in the LIGO lab and the Theoretical Physics and Relativity group, uh, California Institute of Technology. He also was he also received the he worked as postdoctoral fellow at the Canadian Institute of Theoretical Physics, and as well as the Cornell University. He had several awards and scholarships received throughout his career. Some of them I would like to point out. He received the Princess of Asturias Award for Scientific and Technical Research of Spain. He also received the Gruber Cosmology Award Prize from the Gruber Foundation. He received the Special Breakthrough Prize in Fundamental Physics uh, from the and then he had several awards, fellowships such as the Sita Fellowship from Canada, Toronto, Canada. He received the Merit Scholarship from BITS Pilani. He also received the Singapore Airlines Youth Fellowship Scholarship from Singapore Ministry of Education, Singapore. In fact, he has been quite active in the field of research and right from his school days. So we have a very eminent scientist and uh, in the who will be giving a talk in this field on the topic of challenges in computational physics, astrophysics with black holes. So thank you very much for being a part of the program. Over to you, sir. Praise, sir, please.
Thank you so much for that very generous introduction. Hopefully, you can hear my voice and see my screen. Um, Hello. Yeah.
Hello. Are you able to?
Are you able to voice?
Uh,
See my
we,
screen?
we are not able to hear you.
Hello.
Yeah, the volume is too low.
Okay.
Is there any way to increase the? There is an option to increase the volume in
Okay.
the setting.
Yeah, I'm just trying to do that. Sorry about the
Yes.
trouble. I just had a power cut at home. So can you hear me now? And can you hear me
Uh,
better than before?
uh, Maybe you can use the if you go to the option for audio, there is an option where you can use the built-in audio system for microphone.
Okay. I just did that.
Yeah,
Is it
yeah,
better?
it's better, much better now. Thank you.
Okay. Sorry for that snuffle at the start. And thank you very much for the very generous introduction. And so my name is Peyush Kumar, and most of my work has been in the field of gravitational wave astrophysics and trying to extract information from the gravitational wave detectors observations that have been happening over the last 5 or 6 years at the moment for now. And my work essentially is at the interface of computational astrophysics and data analysis. And today I'm going to talk about how we can use computational astrophysics to build up our understanding of what we are observing out from our telescopes and observatories. So to start with, note that most of the stars in the universe, almost half the stars in the universe, they exist in two body systems. And these two body systems are bound, and they which somewhat look like this. And these stars keep rotating around each other and go through the entire lifetime as a two body system, till the point that one of the two stars they lose their fuel and they explode, at which marks the end of the life of a star. And what remains is the core of the star, which promptly collapses to a black hole. So then what forms of the system is a binary which has a star and a black hole in it. The other star also subsequently goes supernova again at the end of its lifetime when it exhausts all its fuel. And then we are again left with a binary of two black holes. And these two black holes, they form some of the most strongly dynamical gravitating systems in the universe, right? So what happens is then at that when we have these two black holes, these then continue to evolve. Now individually they will not evolve anymore. So black holes don't have any fuel, they don't have any evolutionary future beyond that of interacting with yet another black hole. So they continue to stay in a two body system and emit gravitational waves, which are essentially ripples in the space time that propagate outward from these sources. And through these waves, they also emit energy. These waves carry away energy, and that energy comes from the orbital energy of the two body system. And so the orbit keeps shrinking and shrinking and shrinking till the point that the two black holes eventually collapse into each other. And once they, at that moment, this is what it looks like. This is the first, this is a picture of a numerical simulation showing the first instance at which the two black holes have merged to form a single, highly dynamical, highly distorted black hole. And this black hole continues to rotate along its along an axis of symmetry, and it radiates away all of its asymmetries as gravitational waves, and ultimately ends up as a nice curved black hole, a nice curved single black hole. So these gravitational waves that are emitted throughout this process is what we hope to see on Earth through detectors such as Laser Interferometer Gravitational Wave Observatory, or LIGO, and Virgo detector. There's also a LIGO India coming up, hopefully in a couple of years time scale. And there is another detector being developed in Japan that is due to come online in just 1 year's time scale. So this is quite a growing field, and it all started in 2015 when we made the first observation of two black holes hurling into each other. Since 2015, we have seen a ton of such black hole collisions through the eyes of gravitational wave detectors, right? And so here in blue are shown the binary black hole systems that LIGO has seen so far. On the y-axis here are the masses of these systems. And for example, if you take this leftmost one, you have the two black holes that are each around 30 times the mass of sun, or around 18 times the mass of sun. And then they merged to form this black hole, which is around 40 times the mass of the sun. And the difference in the mass between the final black hole and the sum of the two black hole masses got radiated away as gravitational wave energy, right? And the same is true for all of these black holes that we have seen. So the heaviest that we have seen is around 70 solar mass and 85 solar mass black hole, this event here, colliding to form a nearly 155 solar mass black hole at the end of everything. And this is the blue, or in blue are all the black holes that LIGO and Virgo have seen in the past 6 years. In purple are those black holes that had been seen before the gravitational wave window was opened. And how were they seen? So these were seen as two body systems where you have a black hole and a star orbiting the black hole. And when you observe them through in the electromagnetic spectrum, you find that a star is essentially moving in a circularish orbit, and it obeys certain orbital dynamical constraints. And from those constraints, you figure out there must be an invisible entity also in orbit with the star, and that rather invisible entity is probably a black hole. And so these purple ones are those inferred black holes that had been seen before LIGO and Virgo came online. Also, another class of sources that are interesting to LIGO are neutron stars. And neutron stars, again, we have LIGO Virgo in the gravitational wave spectrum has only seen a couple. So these orange ones, whereas through electromagnetic observation, many individual neutron stars have been seen before. And that is because neutron stars do emit radiation. They sometimes can be the sources of periodic gamma ray bursts that are often seen in the sky and can be used to localize the source and characterize the source and study it as a neutron star. So all of these observations are again in the electromagnetic spectrum. Only 4 the orange ones are in the gravitational wave spectrum, right? So clearly we can see that it is really the high mass black holes that form the bread and butter of gravitational wave astrophysics at the moment. We see simply too many of them. Now imagine, now let's look at 3 particular events and the signal that we saw from them. So let's look at this figure right here on the right side, and we see the signal observed from the first three events that were seen in 2015 September, 2015 October, and 2015 December, in order of increasing, or rather, sorry, decreasing binaries mass. So one thing to notice immediately is that the more massive your event is, the more loud is the amplitude of the gravitational wave signal that was seen from the event, but the shorter is the signal. Whereas the lesser massive the source is, the signal is longer but has an overall smaller amplitude. And so if we keep seeing only heavy black holes, then what we will end up seeing are these short signals that are quite loud, right? So that means what we will see is the last few orbits of the signal right before the black holes collide into each other. And at that moment, that is the most dynamical moment in the whole process, right? So the space time is the most curved, time is the most warped, right when the two black holes are extremely close to each other. And that holds true till the moment the two black holes have actually collided with each other. And in these signals, this peak of amplitude here at the end marks the point of collision, right? So for the heavy black holes, what we see are the most dynamical, truly dynamical space-time waves. And to study them, it is simply not enough to use analytic methods that are approximate by nature, or even perturbative methods, no matter how high you go in the order of perturbation theory that you use to solve Einstein's equations. Okay, so now this is how numerical relativity enters, which is a subfield of computational astrophysics. Except in this field, we try to do all our calculations in full nonlinearity of general relativity, without trying to make any approximation of any kind about the background space-time. Numerical relativity tries to solve for whatever system you are studying, but in full general relativity. So if we look at the role of numerical relativity in traditional gravitational wave astronomy, at the top left, we have the compact binary source that is emitting the radiation out there in the universe. And we have our detectors here that actually observe these gravitational waves and convert them to those nice time series that we saw in the previous slide. Okay, sorry, 1 second. For some reason, my screen has frozen. Yeah. So the data coming out of these instruments are, first of all, looks somewhat like this, except these signals in that data are drowned out by instrument noise. And in fact, the noise is the dominant component in this data. The signals are simply too small in amplitude. So we need to really dig them out of noise to figure out even if they exist, and if they do exist, what are the sources that are generating those signals. So we need to do a couple of stages of different data analysis um, measures are applied to the data to figure out if a signal exists to begin with. The first of them is called match filtering, where we take a set of all the possible waveforms for all different combinations of black holes and black holes and black holes and neutron stars or neutron stars and neutron stars colliding with each other. And we take this giant set of waveforms that are possible and derived from some theoretical approximation. And we use them to filter the time series data coming from the detectors. So this is called match filtering, where you have some noisy data, but you know a template of what you are expecting in it. So you take the template and try to match the template with the data. And if something actually exists in it, it shines. If it doesn't look like your template, it doesn't shine as much. But then we have to do a signal consistency stage, which is a more refined, it's a more of a refining stage to finally find out if the data has only noise, in which case what we will find is a distribution of these several triggers that come out of the two stages, which follow pretty much a Poissonian state distribution. Or if there is actually an event which should stand out much above the background of noise triggers that come out of these two stages. And finally, once we have found an event, we have to go back and do a thorough parameter estimation analysis to figure out what exactly were the source parameters of the black holes, what were the surrounding situation around those black holes or neutron stars that led them to merge and emit gravitational waves, and what all can we essentially say about the source of that signal. And in all these stages, knowing the templates is critical, which is where numerical relativity actually enters. So typically, these templates are informed by waveform models, which will come through approximate approaches. But for heavy black holes, where we really need to model the last several orbits before merger, where the space-time is extremely dynamical, all of our approximate schemes, they break down. And we need numerical simulations, exact numerical simulations in GR of black holes to inform these waveform models that are then used in all stages of gravitational wave astronomy. Okay. So numerical simulations are in fact necessary for black hole science. Without having numerical simulations, many of the events that we have seen so far would have probably have been seen at all. And even if they had been seen, many of our measurements would have been simply a lot less accurate than they have been so far. So for example, here for the very first event, we show the measurement of the final black hole's mass on the x-axis and angular momentum on the y-axis, given some approximate models, and the black contour shows the measurement given information from numerical relativity. And you can already see that having in our information improves our measurements by a substantial amount, right? So that's the motivation for doing numerical relativity, or rather for doing computational astrophysics in full general relativity. So now let's look at some of the output of these numerical simulations of black holes that we do. So for example, here we simulate the source of the very first gravitational wave event that we had seen. In the outer region, you will see the gravitational waves being emitted as the color. You can see these outgoing spirals here. In the inner region, what we see in this region, the color shows the space-time, the time dilation, and the depth here shows the spatial curvature. So space is very warped near the two black holes. These are the two black holes. And the arrows here show the arrows of time, essentially. All future directed rays are going inside of the horizons, right? And so we can see the black holes orbiting each other. And at the bottom panel here, the trace being swept out is the gravitational wave signal that is being emitted by this process, right? And we slow down a little bit right before merger. to see how the spatial curvature changes quite a bit. And at this point, we see a common black hole has formed, which quite promptly settles down to a single Kerr black hole. Okay, and you can see as we zoom out the gravitational waves that had been emitted. So let me actually play this again for the benefit of the younger audience. So yeah, and one more thing that I forgot to mention is you'll notice that this plane actually changes orientation. That's because the two body system is rotating and it's precessing. The plane of their orbit is actually changing in space. It is also rotating. So that would be equivalent to saying that their orbital angular momentum is going around the total angular momentum vector with a periodicity that is several times the orbital time scale here. Okay, so at this moment, notice that three horizons existed in this picture. And look at the high curvature waves being emitted here, the really loud gravitational waves being emitted here. So again, here is a simulation where we will show a black hole. This is a more primitive movie. But what it will show is this black hole and a neutron star in orbit around each other. And what we will see is that the black hole will tear the neutron star. This is called tidally disrupt the neutron star and then essentially swallow all the matter around the star. If we had let the movie go on longer, I mean, then we would see all the matter actually eventually reaches inside the black hole and stays there. Okay, so now how do we do so? Numerical relativity, we start with GR and Einstein's equations, and in Newtonian gravity, the equations of motion are rather simple. You have the second derivative of the gravitational wave potential that comes from the density of mass inside an area, and the acceleration of any body is given by the potential, the derivative of the potential at the location of that body. But in Einsteinian gravity, we don't have these concepts. What we have is the background space time is itself a manifold, and this manifold gets curved depending on how heavy an object is. So our sun will curve it. If it curves it visually speaking this much, then in on a similar scale, a neutron star, which is more maybe as just as massive but significantly smaller. So a neutron star of the mass of the sun is going to be around 10 kilometers in radius. That's it. And that would mean that one can get much closer to the neutron star than one could ever get to the sun without entering the sun. So the gravitational curvature is actually the space is much more in terms of for a neutron star, and of course it's infinitely more for a black hole, right? And the geometry around these objects is given by something called a metric, which tells you how much distance has actually uh, if given two events in space time, what is the true distance or what is the light's traveling distance between them. And this metric is what is governed by Einstein's equations, which are essentially um, um, which can be written down in the form of this, where this is the Ricci uh, tensor written in terms of the space-time metric, and on the right hand side should be the energy momentum tensor of the system in question. But if we are talking about purely black hole systems, they have zero angular zero energy momentum tensor in pretty much the entire space time, except at the singularities at the center of each black hole. So the right hand side remains zero everywhere except those two centers. And the Ricci tensor can be expanded into in terms of Christoffel connection symbols and so on, and where these connection symbols are essentially first derivatives of the space-time metric. So what I'm trying to show here is that this tensor here is contains several second derivatives of the space-time metric. So that's the nature of this tensor. Now, the first time people tried to solve Einstein's equations numerically was actually quite early in 1964. And they were able to perform almost 50 time steps, of course, before the simulations crashed. But it turned out it was no easy feat, actually. It took 40 more years of several groups working in tandem and in competition with each other to finally arrive at the very first successful binary black hole simulation in 2005. And this was performed by Franz Pretorius, who's now a faculty at Princeton. And he was able to simulate the last few orbits for an equal mass binary black hole system right before they merged. And so this figure here shows the trajectory of the two black holes at different numerical resolutions. And on the right hand side, it shows the second derivative of the gravitational waves emitted by that system. So this was a relatively short simulation. Soon thereafter, many other groups were able to actually successfully perform simulations. So 2006 saw two independent groups performing this first simulation. So how do we solve Einstein's equations? I mean, we have a single concept of space-time. We have some imagination of what the initial conditions of the problem are, but how do we solve a set of equations is not entirely straightforward. So let me walk people through how basic schematic of the algorithm and the analytic approach rather. So what is first done is we take these four-dimensional space-time equations and we break them down into space and time. We treat the spatial coordinates and time coordinates differently, which is different from what Einstein intended, but then this is how we can perform numerical simulations. So we slice the space into different time slices, and we take our initial data from one time slice and evolve to the other and so on. And in doing this, what we find is that this simple equation turns into these four equations where we have time derivatives of the spatial metric, the spatial curvatures metric in each of these time slices. So G is quite local to these blue planes, and K is the extrinsic curvature of these time slices as they are embedded in the full four-dimensional space-time. So these are three-dimensional slices, but they might have their own curvature when they are embedded in the full four dimensions. That is what extrinsic curvature measures here, K. So these equations tell us how to evolve G and K from one time to another. But what we find is we get another set of equations that simply have no time derivative, but have a lot of spatial derivatives. And they again involve these two variables. And these must remain satisfied at all times also. So these it's much easier to understand this, and if you think of an analogy with Maxwell's equations, where you have electric magnetic fields time evolution given by the curl of the other field, but you also have these constraint equations, which of course don't tell you how to evolve the electromagnetic fields, but they must remain satisfied at all times. So what makes these simulations challenging? So first thing is, of course, there are many length scales in this problem, right? If you take the size of the black hole as the unit of your length scale, then separation of the two black holes is 10 times that unit. The gravitational waves being emitted is approximately have a wavelength of 100 times that unit. And the whole simulation box or the whole domain in which you simulate must be at least several orders of magnitude, I mean, several times the wavelength being emitted to at least record a few complete waves. And that means we have about 10 to the power 3 difference between the smallest and the largest time scales. Now, other problems include which coordinates to use. It is not clear what coordinates will satisfy a given space-time, since we don't really know that space-time quite yet. And our coordinates are very geometry sensitive, right, in general. And so is the space-time in our problems. The space-time is actually evolving the geometry. And so laying down these coordinates takes somewhat of trial and error. Now, putting black holes on a grid in a computer is, of course, tricky, because they have infinities at their center, and computers don't quite like that. Then the main problem that remained unsolved for a bulk of those 40 years from 1960s to 2000s was that these constraint equations, these equations, if we started out with a solution at the initial time which satisfies them, no matter what people tried, it turned out that they became unsatisfied as they moved further on in time. And these violations of these constraints, they grew away from zero exponentially with time, simulation time. And this was a key challenge that was pretty much the last challenge that had to be overcome before the first successful simulations were performed. Then again, resolving shocks, if they form, for example, if you have neutron stars, when the two stars collide, their surfaces lead to shock in the surface touching leads to shock formation in their bodies, and that leads to discontinuities. And of course, the computational challenges are not the easiest. I mean, we have at any moment up to 40-50 variables in which we are solving partial differential equations. And if our length scales and time scales are small, then our time steps are small, which means the overall computational cost is extremely high. And the accuracy required by LIGO is also very good. But there are some good things that we can do with binary black holes to mitigate some of these issues. And that come from the use of spectral methods, which is what we do. And the code that we have written over the past decades is called the Spectral Einstein code. And it has been in development since 2002. It is a closed source code. Unfortunately, we do have plans to make it open source. It's got more than 500,000 lines of C++ and was written by various people at several of these institutions. Now, what is the benefit of using spectral discretization? It is that now with spectral discretization, you have any field that you're evolving. So for example, if you're evolving the space-time metric, you have the TT, time component of the space-time metric, the time x, the xy, the yz, the time z, time y components. Each of these components can be treated independent of the other and then expanded in some spectral basis. And the benefit of doing that is we are able to decouple the x, or the spatial and temporal dependencies, right? So now the time derivatives only act on these coefficients, but the spatial derivatives simply pass through these coefficients to act on the basis polynomials or basis functions. And since these bases are known by hand, we can solve exactly for these derivatives. So essentially your derivatives are free and entirely accurate in a spectral representation, as opposed to a finite stencil representation, where to compute the derivative, you have, suppose you wanted to take the derivative of this curve here, then you have to take some of its neighbors, create an interpolation function, and calculate the derivative that way. And that the accuracy of that will depend on how many neighbors you take and so on. But in spectral methods, simply it doesn't depend on how many neighbors you take. You can and you don't even need to make any approximation of finite differencing. So whereas the spatial derivatives act on known polynomials, right? So this is what our simulation domain for the two black hole problem looks like. So let's start with this picture, top left. We have spheres tiled around each of these two black holes. Each of the two singularities, for example, one of the two singularities are zoomed in here, and they would lie somewhere inside here, inside the cavity here. And outside we have these spheres. Now, if we zoom out a little bit, we see these two black holes, and these are again what was shown here, only zoomed out. And in between the black holes, we have these conical shaped grids, which correspond to the shape of the physical fields that are varying between the black holes. If we zoom out even further, we see that this near zone or the source area has these truncated spherical domains here. But away from the source, we take again simple spheres. And if we zoom out for the whole domain, we see that the outer part of the domain is again stacked by a set of spheres, right? And you can see how large the domain is as compared to the source. The source is not, it's barely visible at this time scale. Okay, so let's, in the interest of time, let's not talk about um, we can actually talk about the evolution. So we evolve Einstein's equations in a first order form, where we take the second order equations and we reduce them to a first order set of equations. So how do we make that reduction? And the way we make it is we take the first derivatives as now free variables. So the first spatial derivative becomes pi AB. The this is actually the first time derivative, and this is the first spatial derivative that becomes phi IAV. And now we have, instead of just one space-time metric, we have three tensors that now have a set of equations, but first order equations. And these first order equations must are the ones that we need to solve. Now the okay, so these are subject to some constraints that we had already talked about. And these constraints, if you remember, kept on growing exponentially because their evolution equations actually had a term proportional to them constraints themselves. So as you know, I mean, if you solve such an equation, you'll find a exponentially growing term. So what do we so how do we deal with these constraints? I want to just show a quick example. So if we look at, for example, the equation for scalar waves, the second order equation is this one, but we can reduce it to first order by again introducing a time derivative and the spatial derivative as free variables, and we get these three equations. And now we have this constraint that must remain true at all times during the evolution. And if you write down the evolution equation for this constraint, we find that right hand side is 0, which means that if you start with, if for some reason your numerical solution gets a value of c not equal to 0, then the future solution will actually not, will also be erroneous. That error will not go away with time, it will stay there. This is not quite as bad as what Einstein equations have, but it is it will do for the example that I'm trying to show. So what we do is we simply change the original equations by adding an artificial term that in ideal life would be 0, but in, so it changes, not, it doesn't change the nature of these equations, but it does change the evolution equations for the constraints themselves. And just by adding this, we find that now this is what the evolution of the constraint will look like. And because of the minus sign here, we know that even if you start with a constraint violating solution, very quickly your solution will decay and come back to a physical space, physical solution space, right? Because if you solve this equation, you find an exponentially damping term, not growing but damping term. So this is quite what we do with Einstein's equations also. And how do we treat the singularity? So what we do is we place an excision surface around the singularity that is just inside the horizon of the black hole. So this surface is a delicately placed surface that remains inside the horizon but away from the singularity at the center. And this excision surface keeps tracking the singularity and it moves with it so as to never intersect either the horizon or the singularity at the center. And by doing so, we are able to essentially excise out or scoop out the singularities from our domain. Now, we also use a technique called adaptive mesh refinement, which makes our simulations dynamically accurate. And the way that is done is, what that means is that our domain becomes finer and finer as the needs of the problems grow. If the solution, if when the two black holes are far away, we don't need a very refined grid. A coarse grid will work. But when the black holes come closer to each other, we need gradually more and more refined grids around the two black holes to resolve the oscillations in the two black holes' horizons. And this is called adaptive mesh refinement. And this is done by essentially looking at the spectral expansion coefficients of the different fields. And if we find that uh, the, the 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 number of terms that we are keeping in the spectral expansions are getting very large coefficients around corresponding to them, that is an indication of that we need to add more terms in our spectral expansion. The number of terms we currently have are not enough, so we add one once the smallest coefficient goes above a certain value, and that way we can have a resolution. So this figure here shows the refinement level of the grid around the two black holes. So this is the bigger black hole, this is a smaller black hole, and you can see the height in steps is essentially the refinement level or the density of the grid. You can also see the density by the mesh around it, right? You can see the density of the mesh here and here is becoming more and more refined. And near the smaller black hole, we need a more refined grid because the oscillations on that black hole's horizons are very small. So if we were to resolve them, we need smaller length scale, smaller spacings between our grids. Okay, so we'll skip this. Now, an important element of our simulations is, of course, control systems, controlling various aspects of uh, the two bodies, the domain that is following the two bodies. So here, for example, is a snapshot of a mass ratio 10 simulation. This is the red one is the excision surface of the bigger black hole. So it's right inside the horizon, but far away from the singularity at the center. And here, this on the left is the smaller black hole that is smaller by a factor of 10. And this is the tiny excision surface around it. And the singularity is right in here somewhere. And you can see this these surfaces have complicated shapes, and these shapes need to be tracked along as we go along with these simulations. So that is tracking is done through controls using control system theory that is um, often taught as part of engineering curriculum in our university system. And so coming back to all the challenges that I started with, the spec code already finds solutions to the problem of length scales by using adaptive refinement. We find good coordinates to use. We know how to put a singularity on the grid by excising them. We find a good solution to controlling constraints. Yet some of these problems remain unsolved, or rather solved unsatisfactorily, which are we still lack how to do time scales, how to manage different time scales, and we lack the way of robustly handling shocks and robustly, and rather making our simulations quite fast, is something that is not easy with our current spectral Einstein code. So a few years ago, we went back to the drawing board and we realized that these are the 4 key challenges that remained in front of us, right? Multiple scales of time, computational challenges, and yet managing to maintain high accuracy while our simulations are cheap. Okay, so we realized that we need to rethink the entire problem. And in rethinking that, we realized that 3 critical ingredients need to change. And this is something that is of quite this is something that is of quite general interest, not just in numerical relativity, but whenever one is solving problems in computational astrophysics of any flavor, or computational fluid dynamics, or essentially any computational problem which involve differential equations, which a lot of our physics problems are. The 3 critical things that we must consider properly at the start when designing the solution is the discretization scheme we want to use. It should be local at high order. What does this mean? This means that if you want to take a very high order accurate derivative at any point in our domain, we must not need information from our neighbors very far away. That is the case if we are taking finite difference derivatives. That is even the case if we are having global spectral methods like spec, where the entire domain, where you have domains of such large size, right? This entire sphere has one spectral expansion. This sphere has another spectral expansion. So taking the derivatives at this end essentially involve points at this end. This sphere in the blue region again has a single spectral expansion. So taking a derivative here involves information from here, right? So while we can go at very high orders with these spectral expansions in this way, we are not at all local. We don't need local information. We need information from far away. And that is bad, because that means when solving these equations, your calculations will be completely dominated by the cost of moving information from one computer to another. If you are solving it on, say, 100 machines at the same time, you will entirely be slowed down by how much time it takes to move information from machine 1 to machine 53 and so on. So you need to be local. Then you should, discretization should be able to handle discontinuities. It should be amenable to arbitrary shaped grids, right? If you're going to have very small grid elements, then they may have quite unreasonable geometric shapes, and the scheme should allow for pretty much arbitrary geometric cells or subdomains, right? Now again, the parallelization, the way you parallelize, most codes in the world, they use something called MPI, or massive parallelization message passing interface, which is now rather outdated way of actually doing this. And we need to find a different parallelization scheme that can actually scale and use all the computing resources available to us. And finally, use local time stepping in order to handle multiple time scales. Local time stepping means that where you have very fine oscillations going on, fine um, physics going on, small scale physics going on, at that, in those regions, you should evolve the time slowly to capture all the physics. But far away from those regions, there is no need to evolve your equations just as slowly. You can take bigger time steps, and that will save a significant amount of computation, right? So we, if you look at a few different ways of doing discretizing, the first common method is a finite difference method. So essentially your domain is a set of points at different x y coordinates, and the solution is represented as a local polynomial. So taking the derivative requires a stencil meaning if you want to take a second order derivative, you want two neighbors. If you want to take a third order accurate, not the third derivative, third order accurate derivative, you need that many neighbors from both sides. If you want to take eighth order accurate derivative, you need that many neighbors from each side. And so while at low order it is local, it is not local at high order accuracy. It handles discontinuities well, and it does inhomogeneous grids pretty well. Then the spectral methods that I discussed, where solutions are now expanded in terms of basis in different parts of the domain. So here are the first two basis elements, the flat being the constant, the first term, and the slanting line meaning the second term, the linear term. In each basis, these are the first two terms. There can be more terms, quadratic, cubic, and so on. And the problem with, yeah, the solution again will be represented in this fashion. And the problem here is, while it is somehow local at low order, actually I should have marked this red, it is not local at high order. And it does not handle discontinuities very well at all. In fact, it doesn't. If you have a discontinuity, you need to redo the entire spectral expansion everywhere, and that is an expensive operation. And but it can handle arbitrary grids. So this is where spectral methods fail. Then finite volume methods have, in each cell you represent the solution by the cell average. So the way you apply finite volume methods is you make your cell size very small. You have very small and a large number of small cells, and in each cell your solution is simply the cell average, right? So now again, this is local at low order. It is just like finite differencing. But if you want to take high ordered accurate derivatives, just like finite differencing, you will need to contact your neighbors, as many neighboring cells as possible. Which means again, we are stuck with the problem of waiting for your computing machine 1 to communicate with computing machine 12, and 12 to communicate with 33, and so on. And that slows down everything enormously. Now, finally, what we found is something called discontinuous Galerkin methods, where in each small cell or subdomain, the solution is expanded on a basis, just like spectral methods. But you don't require exact continuity between the cells, and you can have numerically prescribed fluxes between the cells. So each cell only takes information from its immediate neighbor, and that's it, no more, not even the neighbor beyond it. This cell will take only information from its immediate neighbor. So that means if you want a higher order derivative, you can simply have a high order spectral expansion in this cell. But it can handle discontinuities because these cells can become very small. Just so you can have small cells around the points of discontinuities, and yet you can still be local at high order accuracy because it never needs information from beyond one neighbor, right? So discontinuous Galerkin methods, if you remember one thing from my talk today, it should be use discontinuous Galerkin methods for solving partial differential equations. Then finally, local time stepping. We already talked about this. So the way we do it is, suppose this is a diagrammatic representation of two black holes. This is a spatial axis and time axis, and the two black holes are here. So near the smallest black hole, we take smaller time steps. Near the bigger black hole, we can take maybe slightly bigger time steps. And far away, we can take further bigger time steps. And in the middle, when we need information from, say, this region or this region, for taking the time step from this step to the next, we simply extrapolate. We extrapolate the solution here to this area, this point. We extrapolated the solution in this spatial coordinates to this time. In time, we extrapolate a little bit in time, and that is enough to calculate the time derivatives around the smaller black hole to take the next step and the next step and the next step and so on. So in doing so, we save a lot of computation. This, however, is a second order improvement. Discontinuous Galerkin methods is the primary improvement that one must seek. And again, the way we parallelize MPI can be harmful because you may have some tasks that are much more expensive than others. The way you parallelize may be such that one task remains much more expensive than others, and if that is true, then the computer that is doing that task will keep all others waiting while it completes. And what is a better way of doing this parallelization is something called task-based parallelization, where the big tasks are actually broken down into extremely tiny tasks. Like each multiplication, each division can be broken down into a task. And then these tasks, they go into some global sort of queue, and these queues are then run against all the computers that you may have. So it never happens that any computer is waiting to do something. What will happen is that if all the work is done by all the computers and only one is slowing everybody else down, all the other computers will contribute to that last one's work. It will take other bits and pieces of that last one's assigned work and complete it to help essentially, and the whole efficiency, it increases significantly. Okay. So this brings us to our new, very recent numerical relativity called Spectre. And Spectre actually is in development, but so far it is proving to be very flexible and very robust in scaling up. So we tested our code to solve some standard problems on 20 computers, 1,000 computers, 10,000 computers, 100,000, and up to 500,000 computers or cores. And we found that as we increase the number of cores, we simply linearly increase the speed up, which is the ideal scenario. This means that you are literally using all the computing that is available to you. This is in stark contrast to current numerical relativity codes, which scale up to about 100 computers. But if you add beyond that, you will not see any speed up because they will get limited by the communication cost. So discontinuous Galerkin is the main reason, and the task-based parallelism. Those two have made the utilization of our computing resources near perfect as compared to the previous generation of computational astrophysics codes. And we'll not talk about that. So finally, let me end by saying that we have this new numerical relativity computational astrophysics code, called Spectre, which is open source. It's available on GitHub, and it is a substantially forward-looking astrophysics code that adopts the cutting edge from all aspects of computing paradigms. And if you remember one thing, as I said, remember discontinuous Galerkin methods and task-based parallelism, right? And these paradigms, they allow us to scale up to, very future, far in the future supercomputers. And so far we have Einstein equations and magneto-hydrodynamics equations. So we can do um, basic hydrodynamics, basic magneto-hydrodynamics, and uh, also now full GR MHD. So essentially hydrodynamics in a gravitational general relativistic background, which is what is needed if you're solving for neutron stars near black holes, right? And some aspects of this code is still in development, but they're nearly there. And we hope for users to be able, students and researchers to be able to use this to solve a wide variety of problems. Could be in fluid dynamics, astrophysics, or whatever they want. As long as, as long as the problems can be posed down in terms of partial differential equations or ordinary differential equations of hyperbolic kinds or elliptic kinds also. And we have made this code open source, and everyone here is encouraged to actually have a look and try. Okay. With that, I think I should stop here and take more questions about what I've said. Thank you so much.
Thank you, Dr. Pravesh Kumar, for a wonderful insight into what one can do with computational astrophysics. Because astrophysics is a field which requires a lot of big experimental setup, which is not possible at every place. But yes, a lot of data is available which can be used to model things and work out using computers. And you have given us a good insight into what can be done, what are the techniques used, what are the methods and techniques used in this. Thank you very much. I would like to, well, the session is open for question and answer. If anybody is interested, if anybody wants like to ask any question, please, you can raise your hands. I can't. Is there anybody? Yeah, there is some question like the techniques that you use here. Uh, are these techniques specifically designed for studying uh, the cosmological events, or are those techniques very generalized? For example, can it be used to study some other kind of system which is not in the field of astronomy, but maybe some other process modeling or things like that?
These techniques can be used, as I said, to solve a variety of physics problems. You can do acoustics, you can do all sorts of wave mechanics, you can do fluid dynamics, and you can do simple relativity, you can do general relativity, you can do hydrodynamics with and without viscosity, with magnetism around it. And so it's essentially general enough to be used for physics problems that can be posed as a set of partial differential equations of hyperbolic kinds, or other equations.
Yeah, definitely.
So that covers quite a wide variety of physics, right? So
definitely, because the techniques, in fact, just learning the techniques because even if somebody learns a technique which is not associated with the astrophysics field, but if they learn these techniques, they can easily apply this in the field of astrophysics or in any other field.
Right.
So, computational physics, computational science is something which is really not much popular among a lot of students. But then to show that this is really a very interesting field, because there are things which one can do work out, which could be next to impossible in the experiment or extremely difficult to perform in the experiment. So getting a very good deeper insight into the experiment is something which can be performed using these simulations. You
Right.
can't go to the black holes and then understand what actually is happening, but then based on the data that is available, one can actually peep into the different things, that is events that is happening in the black hole.
Exactly.
So it's really, yeah.
And even back on Earth, like if you take, for example, the question of how to design aircrafts and wind tunnel testing. Recently, Boeing launched an aircraft where the first testing that they did was a manned testing, and before that they had done and the entire designing and testing of the entire aircraft using simulations, computational simulations. And that is also something that, even Spectre can be applied to. So I'm just trying to emphasize your point that these computational sciences can lead to tool sets that can have an extremely broad range of application, from astrophysics to airplane design.
Yeah. Yeah, madam is there. Yeah. So there are no questions, madam. Yeah, the talk is done, and yeah. Okay, yeah, please, Sham, you would like to, yeah.
Okay,
Yeah,
thank you so
madam,
much.
you can. You can, madam. You are mute. Yeah.
Yeah, thank you. Sorry, I was muted. Thank you, Dr. Piyush Kumar, very much. I was listening off and on because I was a little busy with the meeting. So I heard parts of your talk, and I think it was a very, very useful session for the students. And because usually astrophysics students think is a very hardcore mathematical subject. So it was very important to show them the computational element of the subject. We are very thankful to you for joining and giving this talk at a very short notice, in fact. And we hope that the department will continue to have interaction with you. We have a number of faculty members who are working in computational areas. Dr. Chako himself is working in computational aspects of material science. And then we have other people who are working in space weather physics. And I hope to have I hope they'll have interactions with ICTS and with you in particular, and we'll have some fruitful collaborations through the center. Thank you very
Definitely.
much for joining us.
Thank you very much for inviting me, and I look forward to collaborations. And I also invite all students, if you have any questions, feel free to email me. Thank you.
Thank you very much, Dr. Piyush Kumar and Shadam. We are to the end of the first session of today's program. There was an announcement. Yeah, the next session, there are 3 talks which are of a very general nature, and one of them is based on the Nobel Prize in physics, and we would like all the participants to attend the session. And they are very popular talk. In fact, you can invite your friends, and you can forward this to your friends and colleagues, and ask them to attend the session, because these are very general sessions and very public talk. So could be it can be attended by all. So please, thank you very much for all the participants. We will now stop here, madam, and we'll come back at 2 o'clock. We'll start at 2 o'clock.